Okay, so welcome to week 4 of electromagnetics in guided and wireless media course, which is being offered on NPTEL by Professor Pradeep Kumar from IIT Kanpur. And we are into week 4, and what we are going to study today is how basically the electromagnetic waves uh, behave in a, let's say, certain material systems. We are going to talk about the electric field component, the magnetic field component, and how those components behave as they hit any system. By hitting, I mean when they sort of interact with a certain dielectric or a conductor, what is basically going to happen to these electric and magnetic field components in an electromagnetic wave. And today it will be a different session in the sense that we will be mostly solving the questions from week 4, which will be covering most of the concepts that have been discussed in week 4. I guess in week 4, some of the concepts that have been discussed are related to, let's say, Poynting vector, the Poynting vector, which is basically how much energy does the electromagnetic wave carry. So it has a unit of watt per meter square. So it's basically a sort of energy density, like how much energy the electromagnetic wave carries. Then you might have talked about the uniform plane wave uh, at a normal incidence, and you might have talked about oblique incidence, and then you might have talked about certain scenario like polarizations of the electromagnetic wave. Polarizations of the electromagnetic wave. So all these things that have been covered in this week, and I'm not going to again recap all of these things. Maybe I'll discuss briefly some of them in the questions which we are going to solve, but they are pretty much straightforward in a sense that we can actually deal them in the questions itself. So let's jump straight to the question solving session, and what we are going to do, uh, we are basically going to solve some of the questions that have been maybe it's sort of you can treat them as a uh, sample problems or sample examples which you can consider that is going to guide you basically to solve the actual realistic problems that will be asked in the examination. So let's take the first question itself. So question one says that you have a consider the electric, magnetic, and the electric fields to be this equation, this form, and the magnetic field is in this form, where the amplitude of the magnetic field has been given in ampere per meter, and the frequency is 30 gigahertz. So this is the frequency, and so this is the amplitude. This is the electric field component, and from this electric field component, which is basically y bar, y cap, neta naught, which is basically the impedance of the wave impedance, basically. And wave impedance, we know it's basically the electric field amplitude divided by the magnetic field amplitude. Okay, and or not the amplitude, it's the electric field component divided by the magnetic field component. And you have h naught e to the power minus j k z in volt per meter. So you see that this electric field is basically represented in terms of the magnetic field, and that's why this characteristic, the wave impedance, has been multiplied with it. And this is basically an electromagnetic wave propagating in z direction, and it has a polarization in what is happening, and it has a polarization in y direction. Just give me a moment. So it has a polarization in the y direction. So this is the polarization direction. This is the propagation direction. That is how you basically uh, consider the electromagnetic wave and how you understand it. Now this is for the electric field component. Now what about the magnetic field component? The magnetic field component is basically given. Basically these are vectors, so you have to mention the notation over the top to basically separate them from the other quantities. So you have x cap h naught e to the power minus j k z in amps per meter. So this is the magnetic field. Obviously, it's a magnetic field of the same electromagnetic wave, which is propagating in the z direction. So let's say this is z direction. So if this is the electric field component, then electric field component is oscillating in y direction, and the magnetic field component is oscillating in x direction. So this is, let's say, the x direction. Then the magnetic field component oscillates something like this in the x direction. But both of them, so let me highlight this. So this is the magnetic field component. It's oscillating back and forth in the x direction, but the overall wave is propagating in this direction. Okay, so that is how this electromagnetic wave will look like. But you notice that all of this is in terms of the magnetic field. So electric field has been shown in terms of the magnetic field amplitude. That's why the wave impedance is multiplied. And this is in terms of the magnetic field. Why? Because H naught is here given. You might have to use it somewhere. Maybe I'm not sure. And also the frequency, which is frequency of this electromagnetic wave, which is 30 gigahertz, has been given to you. And the propagation is in free space. So you have a free space propagation. That means it will move with the speed of light in the free space. Okay, so it's sort of a vacuum. We have to assume the lossless propagation. That means there will be no lossy media. So it's a lossless media. And we have to calculate the time averaged power density. So this is the quantity of concern which we need to calculate. So when we talk about this time average power, you might have seen in the lectures, this time average power is directly related to the actual Poynting vector. So this is the Poynting vector, which basically gives you the power density of the electromagnetic wave. And when you average that Poynting vector, you get basically the average power density, which is exactly equivalent to half of real part of electric field component into the magnetic field component, but its complex conjugate. Okay, you might have seen it in the derivations during this in this particular week. So if I, let's say, add a page, I'm going to solve the question 1 here. So let's say this is question 1, and this is how we will approach the solution. So let me just take these things here and remove this. Okay, so we are given everything. What we need to basically compute is the time average power density of the electromagnetic wave. That means how much power is basically moving in this direction. So we need to compute the time average power density of the electromagnetic wave. Okay, so first of all, what will be this H conjugate? So if you compute the H conjugate, that will be equivalent to x hat H naught e to the power j kz, because the conjugate of minus j will be plus j. So that will be it. So you're going to use these values in the average power, which will be half of real part of the electric field is as such, which is minus y naught, which is I guess we missed something. Yeah, okay. So there'll be this will be y naught, y cap, neta naught, h naught, e to the power j k z. This is cross product with x cap, h naught, e to the power j k z. Okay, so when you multiply them both, what you're going to get, this in the z direction. That means this is the crossing of this into this. That means you have to cross x with y. So if this is the cross product, then crossing x and y, you're going to get z. So you are going to get z cap direction. Neta naught will be similar. H naught into h naught will be h naught square, and these two are going to negate each other. So you are going to get this divided by 2 watt per meter square. So this is the average power density with which the electromagnetic wave is basically propagating, and it makes sense. It has to be in the z direction because the power is basically moving in this direction, in the z direction. Okay, just like here, it's moving in the z direction. Now this is basically the time average Poynting vector. So this is not the time average power density. It's the time average it's the time average Poynting vector. Okay. Now the time average power density, you know that you have to use the value. So you have computed the time average power. Uh, it is exactly the density because it's in watt per meter cube, watt per meter square here. Now, if you're going to use the exact values of eta naught, h naught square divided by 2, so you have everything given. Eta naught is basically 377, which is the impedance in free space because you're given the free space propagation. So eta naught is 377 ohms for the free space. So you need to use 377 into how much is h naught? H naught, I guess, was given, which is 25. Okay, so this is 25 square divided by 2. So you're going to get something around 107.81 into 10 to the power 3 watt per meter square. So this is the exact power, average power density flowing in the plus z direction. Okay, this is all flowing in the plus z direction because there's a negative sign here. If this would have been positive, then it was going in the minus z direction. You know the convention, right? Okay, now if you need to compute, this is the total average power, and this total average power is half from electric field and some of it is from the magnetic field. So both electric and magnetic fields constitute the total average power density flowing. So electric field component, the power in the electric field will be, let's say, you write it as P in the electric field component. That will be given by the 1 by 4 mu naught h bar h star. Okay, so this is mu naught h naught square divided by 4, and power contained in the magnetic field, that's denoted as Pm. That will be 1/2 of epsilon naught E into E star. This will be exactly neta naught square epsilon naught h naught square divided by 4. Why this neta naught and why this epsilon naught is coming? This is epsilon naught. This is epsilon naught, the permittivity of the free space. And why are we representing this all in terms of H naught? Because H naught is given in the question. Okay, so it depends upon if you are given H naught or if you are given E naught. Then you have to basically convert the H naught into E naught or E naught into H naught by using the characteristic impedance, the wave impedance. Okay, so you can basically solve this particular thing using the values. Mu naught is basically 4 pi 10 to the power minus 7, and then you are going to use 25 square divided by 4. So what the value you are getting is 1.96 into 10 to the power minus 4. This will be joule per meter cube, and this will be 1.963 into 10 to the power minus 4 joule per meter cube. Okay, you can basically then convert the values, but you see that half of the power is basically uh, contained in the I should say it is contained in the electric field and half of it is contained in the magnetic field. Okay, did we make some mistake? Yeah, I think we made a mistake. This is basically a magnetic power and this is the electric power. Okay, yeah, that makes sense because this we are using the magnetic field components here, we are using the electric field components here. So this is about it. So you have computed in this example, you have seen that both of the magnetic power and the electric power gives rise to the total average power density that is flowing in the plus z direction. Okay, just give me a moment. And now, that this, why did we compute this? Because this is what is basically asked in the second question. So the second question asks, what is the stored energy in the form of electric and magnetic field energy densities? So for the first question, the answer is this part. For the second question, the answer would be in joules per meter cube. That will be 1.96, and this is exactly this. You see that both uh, the electric field and the magnetic field, they basically carry half of the energy or the power of the electromagnetic wave. So this carries half of it, this carries half of it, and accordingly, all of it flows in this direction. And we are assuming the lossless media. Okay, in the question, it was basically given the propagation is in free space and it's a lossless propagation. Okay, so and why is it important? Because if it's not lossless, let's say, then if the medium has certain permittivity and the permeability, then accordingly the magnetic field components and the electric field components are going to face different, I should say, losses inside the medium. That means whenever the electromagnetic wave will hit here, If let's say this is the electric field component and this is the magnetic field component, depending upon the epsilon and mu value, accordingly the electric field and the magnetic field is going to be modified. So the energy density is going to get modified according to the values of the permittivity and impermeability. But right here we consider the lossless propagation, which is not the case, which is the simplest case we are basically considering here. So this is the exact answer of the question. Now moving to question 3. What is question 3 saying? What is question 3? Did we split? Okay. The electric field intensity, so this is question 3 now. The electric field intensity of a plane electromagnetic wave. So you are given a plane electromagnetic wave, which is basically EZ. So EZ is given, it is x cap 8 cos of 10 to the power 6 pi t. So this is basically, so this is cos of omega t. So omega is 10 to the power 6 pi. That means 2 pi times frequency is 10 to the power 6 pi. This goes, so frequency is 10 to the power 6 divided by 2. That is approximately 510 to the power 5 hertz. So this is exactly what it means. And x cap is basically representing its polarization direction, or the direction of its oscillation, and it's propagating in the z direction. Okay, it's the similar, it's like the similar way which I have shown here. Not the similar, here the electric field was in y direction, but here it's in z direction. So it's like a electromagnetic wave which is propagating like this, but this time this is the z direction, and let's call this as y direction. So the coordinates are important, how you represent or how you understand the oscillations of these electromagnetic waves in the coordinate system. Now, so this electric field intensity is basically given at a point, at this particular point. That's why you see this is only time dependence. Otherwise, it should have been cos of omega t minus some kx, kz or kz, because this is flowing in the z direction. But here, if z equals to 0, so it will be only oscillating in time, and it would be oscillating in space, so it is at a particular point in the space. So it's showing that if you have a three-dimensional coordinate system, let's say this is z, this is x, this is y. So at, let's say z at 0, 0, 0, let's call this point P. The electric field intensity is given by exactly this value, this I should say value, which is just oscillating in time, but it's not propagating because we are looking at a particular point in space. Now the magnetic field intensity is in positive y direction, and the wave propagates in the material with properties of this. And this is the conductivity inside the material, which is basically showing that it's a it's a lossy medium, and because it's moving in a material, it's moving in some material with the given permeability and permittivity. So that means the magnetic field is basically oscillating like this, that because it's shown that it's in plus y direction. So this is the plus y direction. So this is the magnetic field, and this is the electric field in x direction. Okay, so we need to compute the magnetic field intensity at a distance of 1 kilometer from the point P in the direction of propagation. So because everything was given at point origin, we need to compute the intensity, let's say at 1 kilometer from the origin. Because it's moving in plus z direction, so we need to compute it in at 1 kilometer in the direction of z it's propagating. So we need to compute what will be the value of the magnetic field intensity at this particular point. Okay, so this is the exact scenario of the question. Now let's take this thing and let's try to solve it here. Okay, so this is question 3. Okay, now what is going to happen? Let's take another page. What's going to happen? You are given everything. I have told you you are given the frequency, angular frequency. You are given epsilon is epsilon naught, mu is mu naught, and you are given conductivity, which is 1.5 into 10 to the power minus 5 Siemens per meter, which is basically certain medium system. You can basically compute the impedance. How you can compute the impedance? It will be under root of j omega mu naught divided by sigma plus j omega epsilon naught. Because it's a lossy medium, so sigma, and so you have to use the sigma value here. So you got to use the mu naught value, which is 4 pi 10 to the power minus 7, you're going to use this epsilon naught, which is 8.85 in 10 to the power minus 12 farad per meter square. And you're going to use the sigma value, which is exactly this. This is Siemens per meter. When you input these values in this particular impedance, you're going to find the impedance value is approximately 342.72 plus J86.5 ohms. So this will be the impedance. You see how much it is closer to the it's closer to the free space, but it's not exactly free space because this is the real part of the impedance and this is the imaginary part of the impedance, which most of the time uh, is basically here because it's complex. Impedance here is complex. So how will you obtain this thing here? You will just multiply it with the denominator. You will just multiply and divide it with the denominator, but with the opposite sign, and then you're going to solve this particular, I should say, complex number. You're going to arrive at this particular complex number. Okay, so this is the intrinsic impedance of the material. Okay, this is the intrinsic impedance of the material. And why we are finding this? Because we need to find the magnetic field intensity at this particular point. And we are only given electric field intensity at origin. So to convert the electric field intensity into magnetic field intensity, what do you need? You need the impedance. Okay. So now because we are considering a particular medium system with certain epsilon naught and mu naught permittivity and permeability, that means what you are going to do, you are going to compute the attenuation coefficients, attenuation and propagation constants or coefficients, whatever you call it, propagation constants. I like to call them coefficients, but let's call them coefficients. You know that the attenuation coefficient alpha is basically the frequency dependent under root of mu naught epsilon naught divided by 2 under root of 1 plus sigma divided by mu naught epsilon naught square minus 1, and the propagation constant or the propagation coefficient is basically under root of mu naught epsilon naught divided by 2 under root of 1 plus sigma divided by omega mu epsilon naught square plus 1. So these are like similar except that there is a sign change here. Okay. And when you evaluate it, you are given everything. You are given this thing, you are given this thing. Sigma is also given, frequency is also given, which is 10 to the power 6 times pi. Then you are given epsilon naught also. You're going to solve this. You are going to add 0.00273 Nepper per meter, and this is Nepper per meter. So this is the propagation constant will be 0.0108 radians per meter. So this is radians per meter because you have used the angular frequency values here, and this will be in radians per meter because this is the propagation constant. Most of the time it's written as 1 by meter, but it's basically radians per meter. Okay, it's just like k, which is the propagation constant, which you write it as 2 pi over lambda. So you can write it as basically radians over meter. That is exactly what it is, how it is. Now the magnetic field intensity, you can find it at some point or a function of z. You can find it magnetic field intensity if you are given the electric field intensity as a function of z divided by the impedance in the material. And at point 0, 0, 0, that means point P, which is this point, basically the origin, you are given the electric field intensity. How much is it? The electric field intensity was given, and it was x cap 8 cos of, which is x cap 8 cos of 10 to the power 6 pi t. You can find h of z as x cap 8 cos of 10 to the power 6 pi t divided by the this value, which is 342.72 plus j86.5. You're going to rationalize, you're going to multiply and divide by this 342.72 minus j86.5 divided by 342.72 minus j86.5. When you multiply and divide by the complex number, what you're going to get is basically you're going to get a certain number. Let's say that you're going to get the certain number. But one thing you need to consider here, because the because it's flowing in the z direction. So if this is z direction, how did we consider the coordinates? This is x direction, this is y direction. So when the electric field is oscillating like this and the magnetic field is oscillating like this, because this is in a material system with a certain material system, it's not a lossless medium, it's a lossy medium. So the electromagnetic wave is going to face a decay in the z direction. So it's going to decay in the z direction, and that decaying factor comes, and the decaying factor is e to the power minus alpha z, where this alpha is basically the absorption coefficient or attenuation coefficient, whatever you call it, attenuation coefficient. So your electromagnetic wave exactly looks something like this. If this is y, this is x, this is z, it looks something like this. And the magnetic field looks something like this. So this is going to exponentially decay in the z direction. Okay, and also because of z direction, there will be another factor which is basically the phase factor. That's why we computed these quantities. This takes care of the absorption inside the medium or attenuation. That's why it's called an attenuation coefficient, and this takes into consideration the phase factor. This is basically the phase factor or the propagation constant. So this phase factor will come, which is basically beta times z inside the equation. So overall, hz is basically going to look, if you keep the impedance as such for now, you're going to basically get the uh, so what you're going to basically get. So pardon me, this is not x direction. This is x direction, but this is basically y because the magnetic field is in the y direction. Okay, this is important. The magnetic field is in the y direction. So this is y cap 8 over neta e to the power minus alpha z is going to come up cos of 10 to the power 6 pi t minus some phase factor which is beta z. So this is the phase factor. This is the attenuation. Okay, now I think you are given everything. Now what you have to compute at z equals to 1 kilometer, that means 10 to the power 3 meters. You're going to use the z value here. What you're going to write at h at z equals to 10 to the power 3 meter, that will be y cap into some, when you solve this particular fraction, this particular thing, you're going to get 10 to the power let's say minus 2.192 minus j 0.554. This is after solving that particular fraction. You will be having e to the power minus alpha z, but alpha is minus 10 to the power alpha is given, but z is 10 to the power 3. How much is alpha? Alpha was 0.00277. When you multiply both of these, you get minus 2.73. Then there is cos of 10 to the power 6 pi t minus 10.8, which is basically beta times z. So how much was beta? This is 0.00108. So multiplied with 10 to the power 3, you're going to get 10.8 ampere per meter. So this is the exact magnetic field at the time varying magnetic field at the some specific point, let's say at this particular point at z equals to 10 to the power 3 meters, which is basically 1 kilometer. So essential thing is that this takes into consideration the attenuation of it in the medium, and this takes into consideration the phase component, which is basically coming because of propagation. So this is the propagation phase that is basically associated with it. So when it propagates inside the medium, there is this spatial phase that gets accumulated in the wave. Okay, now moving on to another question. So what will be the answer of this? It will be 2.192. So this will be the answer of this question. This is exactly the answer of this question. So now moving to the question 4, which is exactly also related to the same question which we are dealing with. So it says that considering the data from question 3, how much faster does the wave propagate if sigma equals to 0? That means if it was a lossless medium. Earlier up till now, this was all for a lossy medium. Why? Because the sigma value was given something in Siemens per meter. You remember this sigma value was given. Okay, now it's considering what happens if there is a lossless medium, how much would have been the uh, how much faster would have been the wave able to propagate? So that is basically governed by the phase velocity you need to compute for it. So in if you have a free space, if you have free space, then your wave propagates with 3 into 10 to the power 8 meter per second. Okay. And if there is a lossy dielectric, let's say there is a lossy dielectric, then your propagation speed, which is basically the phase velocity, will be the frequency divided by the attenuation coefficient. It's exactly the velocity is omega over the propagation constant k. It's the wave phenomena. You write the frequency as velocity into propagation constant. Okay, so and this is exactly 10 to the power 6 pi divided by 0.00108. So you get 2.91 into 10 to the power 8 meter per second. So you see the velocity has reduced. Okay, so the wave propagates. Now we need to compute the percentage. How we are going to compute the percentage? That will be this minus this divided by this. Okay, that is going to give you the percentage. That will be 3 minus 2.91. Okay, so that will be the exact thing. So you need to compute the percentage of it, and you see that it won't be 0% because it's not the same. I mean, if it is 0%, then it doesn't make sense. So the wave propagates faster in lossless media, but sorry, in the lossless media, but it slows down in the lossy media. For how much percent? It's exactly 3.4%. Okay. So this is about it. So let me just quickly give me a moment. So if you yep. So this is exactly the 3.4%. So you basically have 3 minus 2.91 divided by 3 into 100%. So you get 3 minus 2.91, you get this is 9, this is 0, this is 0, so you have 0.09 divided by 3 into 10 to the into 100%. So you get 0.03 into 100, you get this you get 3%. So around 3% value it is basically changing. So that is exactly, give me a moment. I guess this call is going to end in half an hour, and we might have to start the video call again because there's a limitation from Google Meet. Sometimes it pops up. I don't know. See if it's recording. And now let's move to the another question. This was question 4. Now this is question 4, yeah. Now the question 5 is interesting, and it's one of the favorite problems, one of my favorite problems, or one of the favorite sections in the electromagnetics, where you need to deal basically with the exact components of the electric and magnetic field inside the material system. So it talks about, let's say you have let me just add a page. Let's first understand the question here. So you have a plane wave propagating in a free space and it encounters a perfect conductor. So the perfect conductor is here. The electromagnetic wave is coming. So it hits a perfect conductor. Let's say this perfect conductor is a metal. And the essential thing about metal is how it has a huge density of free electrons. And what does the free electrons do? They shield the electromagnetic wave. They don't allow the electromagnetic wave to pass through it. Okay. If this is a metal and if these are the free electrons, at least up to some frequency, it doesn't allow the electromagnetic wave to pass through it. If the electromagnetic wave is coming, once it hits the metal, it just decays exponentially, and that decay is very fast. And the length scale up to which it decays is basically called as skin depth, and it's small. It's of the order of 10 to 15 nanometers in most of the metals. Okay, and there is basically a if you consider the reflectivity or versus the frequency plot for a metal, it something looks like this, where it sharply drops beyond the something called as plasma frequency. So everything below the plasma frequency of a metal, it depends upon the electron concentration and it depends upon the effective masses, the permittivity, but everything below the plasma frequency is gets reflected from the metal. So this gets reflected. That's why metals are shiny. That's why you have so many metallic mirrors, silver mirror, blah blah blah. But this can also be basically solved in a different way. You can also have certain wave which is above the plasma frequency and it will behave differently with the metal. So that's a whole different topic altogether that comes in nanophotonics, how the electromagnetic wave behaves at a nanoscale, and how does it actually interact with the electrons. That's a different topic. But this is exactly what happens. So now the question is that the frequency of the wave is given, which is basically 1 gigahertz, and its amplitude is 1 volt per meter. So when this is basically the electric field amplitude. The electric field intensity is directed in the x direction and propagates in the z direction. So this is basically, let's consider this as z direction, then this is basically the x direction, which we are considering. Let's consider it as x direction. And calculate the electric and magnetic intensities in the material. So we need to compute what will be the electric and magnetic field intensities inside the system, material system. And we know that once it's propagating inside the material, it will be having certain decay, it will be having certain attenuation of the wave. Okay, so now first of all, the if we write if we want to know, if you can see the answers here, just forget about the solution right now. Let me just forget about the solution right now. If we just look at the options here, it is the electric field component and magnetic field component. There is some sine of kx term, kz term, and cos of omega t term, and then there is again sine of kz term and cos of kz term and sine of omega t term, which is basically the space and time oscillating waves. Now, first of all, you need to basically write it in terms of, I should say, you need to find the attenuation coefficients and the phase factors. That's why this is basically beta z. This is basically beta z. This is basically beta z. So you need to find this beta. So what will be the beta one? Let's consider beta inside the phase constant at a given frequency in the free space. Let's say the free space. So it'll be omega under root of mu naught epsilon naught. So it'll be omega over c. That will be equal to 20 pi over 3 radians per meter. And you know that you can write the electric field component as a function of z comma t, as it was given that directed the intensity is directed in x direction, but the wave propagates in z direction. So it's polarized, or the wave oscillations are in x direction. And then there is a how much it is given. Then there is a amplitude of the electric field, sine of beta z times sine of omega t. Okay. So this is exactly the instantaneous electric field intensity. So this is the instantaneous electric field intensity. And similarly, you can write the magnetic field intensity instantaneous as the magnetic field is given in y naught. So you need to exactly consider from this figure. And that means this is basically, let's say, so you see that this is the incident wave. This is the incident wave, and this is the reflected wave. So this is the incident wave, this is the reflected wave. And you see that this is x direction, this is z direction, and the magnetic field is along the y direction, as per this particular picture. That's why we are writing equations like this. So, and this, when it gets reflected, the electric field goes into the minus x direction, the magnetic field is in the same direction, and the propagation direction goes in the minus z direction once it is reflected from here. That is the exact scenario of what is basically given. So you can write magnetic field in terms of the electric field as the E naught divided by neat eta, which is basically in terms of the electric field intensity. Then you have cos of 20 pi, not 20 pi. You can, is the frequency given? Oh, you obtain the beta z. You can write it as beta z cos of omega t. Everything is given. You have obtained the beta. Now you can basically write it in terms of you can use the beta values, which is basically 20 pi by 3. You can find and you have, I guess we missed something. Yeah, okay, there's a 2 factor here, so there's a factor of 2 here, and everything is given. This is again 20 pi over 3, and omega is 10, this is basically 2 pi 10 to the power 9, which is basically given. So as per this, what exactly matches? And the impedance is basically 377, and what we needed to find exactly in the material 1, which is this material, which is free space. So in free space, it is exactly this value. So it's 20 pi by 3, 20 pi by 3, but there's a 2 factor. So the essential answer is part C. So this is the exact answer of this question. Okay, so yes. So this is about this question. Let's okay. So now let's move to the other question. Another important question. Again, this is very important in terms of, I should say, in terms of understanding the polarizations and how you can do it. Basically, this is an electromagnetic wave, which is given by something like this. It has two components, which is, let's say, H0 and H1. So it's composed of the two electromagnetic waves. And it's not a two electromagnetic wave, but it's sort of an electromagnetic wave that's given in this representation. It can have basically a time varying and the time varying and the space varying magnetic field components. How we are going to understand it, I'll basically show you. We have to basically show its polarization. So now, what is this concept of polarization? This is really important for this particular field, and how we are going to solve it. Let's say we are going to simply take this electromagnetic wave, which is the magnetic field component, and this is minus y h naught e to the power minus j beta z plus j x cap h1 e to the power minus j beta z. So it has been discussed in, I guess, the this week's lecture first and lecture second of week 4. And if you pay close attention to how the professor has solved these type of problems, you can see that you have to basically rewrite it in terms of a real part of the uh, electromagnetic wave. So what you have initially, you need to first solve it. What you have basically, you have this component in the y direction, you have this the imaginary component in the x direction. So you have to basically take out this imaginary part. You can write this as minus y h naught e to the power minus j beta z plus x1 h1 e to the power minus j beta z. You can write j as e to the power j pi by 2. Okay, so you can write it as j pi by 2. Okay, now you can just bring it inside. You can have minus j beta z plus x1 x cap h1 e to the power minus j. This will be let's write it as beta z minus pi by 2. It's exactly like this. So now you will take the real part of it only in order to compute the in order to understand the dynamics of this electromagnetic wave. So you will basically write it as real part of magnetic field. And when you write a real part of magnetic field, you know that it will be in terms of the cosine component, because e to the power some minus j uh, omega t minus beta z will have the real part as cos of omega t only. Okay, so it'll be the real part of it, and the imaginary part is in terms of the sine, but we need to see how it goes here. So once you write the real part of it, you can write the real part of this particular component. It will be minus y naught h, the amplitude stays same, and it will be cos of omega t only, plus here also the direction remains same, but what will be different is here will be cos of omega t minus pi by 2, because there is this phase vector. Now you can write it in terms of h naught cos of omega t plus x cap h1 sine of omega t, because theta minus 90 or 90 minus theta is sine of omega t. Because cos is even function, so you can take the negative sign out or it'll get absorbed in the cos. It doesn't matter. So it'll be sine. So this will be h of z. Now the essential thing, how you're going to represent it in terms of a coordinate system. Let's say this is y direction and let's call this as x direction. And let's say z is going somewhere in. Okay. Oh, or let's for a time it's let's say this is the z direction which is either going inside or it's either going outside. But that's what we will be basically also determining. Now you have to take these components separately and draw it on this particular plane. How you will draw it? So let's take certain cases. Let's say this is hz. Let's say this is omega t and this is hz. So at omega t equals to 0, this component will remain and this component will go to 0 because this will be 0. So this will be minus y cap h naught. Okay, at omega t equals to pi by 2, the hz value will be, this component will go, it will be x cap h1. At omega t equals to, let's say minus pi by 2, what will be this cos of minus pi by 2? How much it is? Or it's basically cos of 3 pi by 2. It'll be minus y h cap y cap h naught, and this component will again go at, let's say, omega t equals to pi. Cos pi is negative, so it'll be y cap h naught, and this sine pi is basically 0. And you can go so on and so forth. Now you have to draw it on this particular axis. So for omega t equals to 0, you have hc equals to minus y h naught. So minus y is in this direction, so let's draw it as this is minus y cap h naught, and this is at omega t equals to 0. Then you have at pi by 2, you have x hat h1. So x hat h1 is in this direction, which is basically the length of the vector is important, okay, because that length is essential. So these two lengths are going to be important because we are considering, let's say, h naught, these to be equal, approximately small. So this will be x cap h1 at omega t equals to pi by 2. Now at omega t equals to minus pi by 2, that will be in this direction, in the opposite direction. So this will be again small. It will be of this, it will be how much will it be? Did we mess it up? Let's first draw omega equals to pi. It'll be y. It'll be this thing. This will be y h naught, which will be omega t equals to pi. Then somewhere in the middle at omega t equals to pi by 4, let's say pi by 4, we need a value. It will be minus y h naught by root 2 plus x hat h1 by root 2, which will be along this direction, so it will be along this direction. Similarly at minus pi by 4, it will be something like this. And similarly at the opposite value, I guess we messed up here. Uh, this should be minus x hat h1, yeah, at minus pi by 2. Yeah, so this will be along this direction. This is at minus pi by 2. So this is pi by 4. This is minus pi by 4. So you see how it is going? It's going something like this. And if you draw it, it makes these oscillations basically make a ellipse. So this is exactly how it propagates, and it's good to visualize it in basically a MATLAB or some visualization tool, how basically the polarization looks like. And this is something called as right circular polarized wave because it's moving something like this. If it would have been something like this is basically left circular polarized wave. Okay, and a linearly polarized wave, which is basically a linearly polarized wave, it's a special case of elliptical polarization. It's a special case of elliptical polarization. That means if you have a ellipse like this, if these two bands just come closer, it will form a linearly polarized wave. Something like this, or if these two bands come closer, it will form something like this. This will be a linearly polarized wave. So basically, elliptical polarization is a general concept of the polarization. All other things can be taken from it because ellipse is general. Even you can get a circle from ellipse instead of having this the major axis and the minor axis of the ellipse. If they both are same, the major and minor axes are same, you get a circle. And this will be basically left circularly polarized if the rotation is in this direction, and it will be right circularly polarized in the if the rotation is like this in this direction. Okay, because for the circle you cannot have a shape like this and this. It will be both same. That is the exact concept. Now, whether you have a circularly polarized, you have a left circular polarized or right circular polarized depends upon the direction of how the vectors are moving, and depends upon if it's a left circularly polarized, elliptically left circularly polarized. I should say not not this is basically this is right elliptically polarized, REP, I should write. This is left elliptically polarized. This is right circularly polarized. This is left circularly polarized. And all of them can be understood from the elliptical polarization. So elliptical polarization is more sort of a general. Okay. If we take one more example, because these examples are really important. One, if for example you have if you are given the electric field component, let's try to analyze it a little more. If you are given the electric field component, which is basically given something like x cap ex0 plus y cap ey0 e to the power minus j pi by 2, and this is at z equals to 0. Then once you write the real part of it, you are basically going to write x cap. Let's consider ex0 to be equivalent to ey0 to be equivalent to amplitude A. So you are going to get A cos of omega t plus y cap A cos of omega t. There will be phase factor, which will be omega t minus pi by 2, because there's this phase factor. Okay. Now again, if you want to draw it, you need to take two x's. If you take two x's, you take, let's say this is y, this is x, and this is the z axis. Now again, you draw the similar set of a table. Let's call this as E, electric field. This is let's say this is omega t. This is electric field, and let's draw it for certain values. For omega t to be equivalent to 0, this will be 1. So this will be cos of minus pi by 2. So it will be exactly, so cos of pi by 2 is 0, so only x component will remain, so this will be along this direction. So this will be x cap A at omega t equals to 0. Okay, so this will be x cap A. Now at omega t equals to, let's say pi by 2, you know that this will vanish. This will go to ya. That means it will be y times A. So it will be y times A. So it will be something like this, y times A, and it will be omega t equals to pi by 2. Similarly, at omega t equals to minus pi by 2, it will be like this. Omega t equals to pi, it will be something like here. And once you draw it in this direction, basically the vectors are moving something like in this direction. Okay, why it's moving in this direction? Because the 0 comes here, then there is pi by 2, then there is pi, then there is 3 pi by 2, then there is again 2 pi back. So this is forming like a circle, and this is exactly something called as, because it's moving in this direction, so it's a left circularly polarized light. If it would have been moving in the opposite direction, just like this direction, then it would have been the right circularly polarized. And how would you get that? You just have to use the sign of e to the power j pi by 2 here. That means this phase vector exactly will convert it into right circularly polarized light. So it will convert a left circularly polarized to a right circularly polarized light. That's what basically certain optical equipments or optical components do, something called as phase plates, or they are basically called as wave plates. They give a certain phase shift to the electromagnetic wave, and that phase shift basically converts a one set of polarization to another set of polarization, and they are called basically polarizing wave plates. Or you might have, if some of you are interested, you can just look at most of the time we use these optical components in the optical experiments. And this is the exact, I should say, the background of it, which basically comes from the solving of these real and imaginary parts of the equation. Okay, now I'm going to end the meeting for now, because it will be ended soon in the middle of it, and I don't want to go it like this. I'll be restarting back the meeting in a few minutes. So let's stop the meeting. I don't know why it's still showing me 4 minutes. I think I need to. I think I need to create a different link now. I'm not sure. I don't know if this should happen. Okay, so hope this will work this time. Okay, this worked. So the answer of the previous question, which we were talking about, is basically write elliptically polarized light. I told you about when it will be linearly polarized, it will be just in in the xy. If you have the y and x and this is z, it'll be something like either this or this. That will be basically linearly polarized light. But if you have components, different more components, it will oscillate something like this, and it will be elliptically polarized. And if you have both of these vectors as same, then it will become a circularly polarized light. But that's why I told you that the general concept is basically the elliptically polarized one. So the elliptically polarized is a general concept. Okay, so so let's remove this. So the answer is elliptically polarized light. So let's take this particular thing. Let's take this particular thing. Okay, so now what are the other questions? Just give me a moment. Now you have a uniform plane wave, which is basically given in the question. So, so you have a uniform plane wave in air that is incident on a dielectric slab of this relative permittivity, and the permeability is this. The permeability is given, and you have a sort of conductivity value in Siemens per meter is basically 0. Okay, and let's draw it first. So you have a dielectric slab, something like this. Is incident on a dielectric slab for z greater than 0. That means z is basically in this direction. So this is z equals to 0. This will be z greater than 0 direction. Okay. So this is a slab, and epsilon r for the slab is 2. Mu r is basically 1. Mu r is basically 1. So now you have a electromagnetic wave. So this is a very interesting problem because you can basically understand a lot of things from it. So you have tan cos of omega t minus 2x minus 4z y cap volt per meter. So a couple of things. This basically the direction of the oscillation of the electric field component, which is in the y direction. And you know that this is actually omega t minus kx or omega t minus kz or beta z, whatever you call it. Okay, so what you do is that you compare these two. You have omega t minus kz. So this is basically this particular component, but you take the negative sign out. And once you take the negative sign out, you are going to get cos of omega t minus of 2x plus 4z times y cap. So this is exactly the electric field which is given. So this is k. So this is the k incident direction. Okay. So this will be k incident direction will be basically 2x plus 4z. Okay. That means kix. So because this k incident can be solved into, it can be basically divided into two components. This is kix. So this is basically a directional unit vector. So this is kix and this is kiz. Now when you draw it, how you are going to draw it? So let's say your wave is incident, something like this. So you have an incident wave coming in, which is k incident. Why it is like this? Because it is from this k, the incident vector. The incident vector is not along x direction or z direction. It's along x and z direction. And when it's along x and z direction, it's at a certain angle, which is basically theta I, angle of incidence. So when you draw the normal, it has certain angle, theta incidence, and that theta incidence is basically this, which is basically kiz divided by kix. So this theta incidence can be found tan inverse of 2 by 4, which is basically tan inverse of 1 by 2. This is around 26.56 degrees. So that is how you find the incidence angle. Okay, so that means that this is oblique incidence. So this is certain incidence. This is basically electromagnetic wave coming obliquely. Now, because this can be divided into two components, the kix and kiz, so you can have a x component. Let's say this is x direction, this was z direction, then the y direction is basically going either in or out. Then let's say this component was x direction, which is basically this is z direction, kiz, and this is x direction, kix. So this is exactly how the electromagnetic wave is coming. But this is only the electric field component, and these are all vectors. Once it hits the slab, it undergoes transmission, or what you call as refraction, because it will undergo, let's call this as theta transmission. The transmission k will be along this direction. So this will be k transmission vector, and it also can be divided into two components. It will have a z component, that means ktz, and it will have an x component, that means that means ktx. Okay, so now because if this is theta t, then this angle will be also theta t. And now what you have to obtain this particular system. So scenario of you have to obtain theta t. Another thing is that once it gets transmitted, one part of it goes reflected, and this is theta reflection. And once it goes theta reflection, this will be the k reflected, which will be basically the reflected propagation constant in that particular direction, and it can be again divided into krx and krz. So this is the exact scenario of the electric field going in this particular direction. Now, what we are supposed to find is we were supposed to find the polarization of the wave. Okay, polarization of the wave is a simple thing here. What we can find basically, because you are given that the electric field is flowing as a function or something given like this, and you have a k which is flowing, the incident wave, which is basically in x and z direction, that is in basically xz plane. So hence if this is, let's say, if this is the oscillation is in y direction and the propagation is in this direction, so this is the y direction, This is clearly, if this can be resolved into two components, so this is the electric field incident, this is the K incident, this is the K incident in Z direction, this is the K incident in X direction, and this is Y. So it's the electric field is oscillating perpendicular to the to the I should say the polarization is basically perpendicular to the direction of propagation. So hence it's basically a transverse electric wave. So it's a transverse electric wave. Okay. Uh, Now what is basically happening? We need to, from question number 8, we need to find the angle of incidence. That's why we did this much work to obtain the angle of incidence. Angle of incidence is basically 26.56 degrees. That is basically your question 8. And I want to discuss some more things in this. So you see, I think the next question is also related to it. You see, you have to find the reflected electric field. That means you need to also obtain this. Okay, but one important thing is that the incident the wave vector in the z direction gets flipped once it's reflected. Once if it's transmitted, it doesn't get flipped. It remains same. But the x component remains same here in this direction, in this direction, in this direction. Only the z component gets flipped. Okay. So how do we now proceed with it? If we have, let's say, the I should say we had the k incident, we can write k reflected as the same 2x cap but minus 4z cap, because now the z is in opposite direction. So this is in this direction. This was in this direction, the z component. So now you have the k reflected vector. So you have another vector now, which is k. So you just have k reflected, which is basically equivalent to 2x cap minus 4z cap. You can find theta reflected as tan inverse of minus 4 divided by 2. Okay, so let me just if we wrote it correctly, yeah, this is the exact correct representation. Now, what we are going to use basically, what we are going to use is at this particular interface, you're going to use Snell's law. Snell's law is basically comes from the conservation of, or I should say, the boundary conditions of the electric and magnetic field components, the tangential and the perpendicular direction of electric and magnetic fields. But if you use Snell's law, that means n incidence sine theta incidence, that will be n2, and transmitted or refracted sine of theta transmitted. What things you are given? Ni is 1, basically the outside here is 1. So sine theta incidence was sine of 26.56 degrees, what we obtained, basically this. Then transmitted is basically epsilon r. So the slab's refractive index is square root times epsilon r. That means it is square root of 2. So this will be square root of 2. Then so there is sine of theta t. So we need to obtain sine theta t. So sine theta t will be equivalent to 18.43 degrees. Okay. So this is the exact value of it. And now what we are going to obtain is, just give me a moment. Now what we are going to obtain is the reflected component. How much will be the reflected component of it? We have now obtained the theta t, that will be 18.43 degrees. Now if you find the transmission coefficient, which will be basically which will be basically the reflected part divided by certain certain if you talk about the in terms of the impedances, you can basically obtain the reflection coefficient, which is which you can write as gamma, or even you can write it in terms of, yeah, if you can write the reflection coefficient for an oblique incidence, you can write reflection coefficient for oblique incidence, which is basically eta t cos of theta I minus eta I cos of theta t divided by eta t cos of theta I plus eta I cos of theta t. This is basically reflection, and these are impedances of the transmitted media, incident media, transmitted media, incident media. So this is exactly same what I basically talked about earlier when you had the impedances. When the electromagnetic wave hits a load, which is RL, and you get a reflection, so you use to compute reflection coefficient there. And how much was that? Z1 minus Z2 divided by Z1 plus Z2. And these were the impedances of the line, impedances of the load, so on and so forth. So this is exactly the same form, except that here it's an electromagnetic wave and it's hitting at oblique incidence. If this is not an oblique incidence, then basically the reflection coefficient for the normal incidence basically falls something like it becomes eta t minus eta I divided by eta t plus eta I. This will be the reflection coefficient because in that case the incident cos theta I will be equivalent to it will be 0. Okay, that means if the wave is coming something if you have this as normal and you have the wave coming something like this with a certain theta incidence, then this particular equation gets is valid. If the theta incidence becomes 0, that means the wave comes something like this, and theta incidence will become 0 degree because it's exactly falling in the same plane as the incident as a normal of this. Then this equation becomes valid, and most of the time you might have seen these equations because they consider the normal incidence. Now we have the oblique incidence, and what we are going to suppose to find here, everything is basically given. We have obtained theta I, we have found theta t, uh, eta eta t and eta I are basically given. So eta t is 1 over square root of 2, which is basically 1 over under root of epsilon naught mu naught. Epsilon and mu. How much were epsilon and mu? So this is eta transmitted, which is basically the slab's impedance, which is 1 over square root of epsilon r mu r. So it will be 1 over square root of 2. And eta incidence is basically 1 over under root epsilon naught mu naught. Okay, so let's treat it similarly. So you can write it as 1 over square root of 2 cos of 26.56 degrees minus cos of 18.43 degrees divided by mm, divided by 1 over square root of 2 cos of 26.56 degrees plus you have a cos of 18.43 degrees. So this is such a so much calculation to do. When you obtain the reflection coefficient of minus 0.2. Okay, now you know that the reflected component amplitude will divided by the incident amplitude will be equivalent to the reflection coefficient. So you can find the reflected amplitude as reflection coefficient times E incident I, which is basically the amplitude of the incident component. So this will be minus 0.2 into 10. Where does 10 come from? Because it's given here, the 10 is the incident amplitude. So you can get as minus 2. So this is the reflected amplitude. And now you can find the reflected electromagnetic wave in the as in equation form, in the oscillation form, as minus 2 cos of omega t minus it will be basically 2x. This is actually 2x minus 4z. Okay, remember the z direction flipped. This is the z direction, it is minus z. So this is exactly like this into a y cap. And it's the oscillations are still in the same direction. Yeah. Okay, in the y cap, because this is y inside, going inside. Okay, this is y. So now you can write ER as minus 2 cos of omega t minus 2x plus 4z y cap. So this is the reflected electromagnetic wave, which is basically minus 2 omega t. You see that there will be a trick here, which is basically minus 2x plus 4z, minus 2x plus 4z. Minus 2x plus 4z is the answer of this question. Minus 2x plus 4z. So this is the exact answer of this question. This is the exact answer. So there'll be a trick sometimes they play, because if you don't take negative sign out, then you will be trapped here and you will sometimes write it wrongly. So you need to be make sure that you're writing it as omega t minus some sort of kz here. And you need to take consideration of the sign here. This is not exactly kz. this is actually k vector, which is basically incident vector. So this is exactly k incident. So this is sort of a k incident vector. And if it's in z direction, then it can be z. If it's in some other direction, then it can be in terms of x. It can be in terms of z. It's basically a vector. Okay. Now, now what we have done, we have obtained the reflected electromagnetic field. Now we need to find the magnetic field. We obtain the electric field, which is basically the reflected component. Now we can find the magnetic field also. How we can find the magnetic field? For the magnetic field, you basically need to have what you call as impedance. Okay, you should have the impedance, but you see that, did we make a mistake? This is 3 square root of 20, pardon me. I guess we missed this thing, but it is pretty much quite clear from the uh, values which we have obtained, which is basically the omega value. So was anything written about the omega? No, but we can find this omega. We write it in terms of omega, but we can basically find, because the the k incidence and the k reflected is given. Let me write. Says yeah. So so you can find it as, because the k incidence is equivalent to k reflected, which is equivalent to square root of 20. So the k can be given as omega under root of mu naught epsilon naught, because you know that k is equivalent to omega over c, and c is the omega over vp, which is the velocity of the wave, and velocity of the wave can be 1 by mu naught epsilon naught. So you can write it as, you can obtain omega from here. You get omega to be equivalent to 3 into 10 to the power 8 into square root of 20. So you get 3 root 20 into 10 to the power 8 radians per second. So we were missing this particular detail. So this is basically the correct thing. 3 root 20 into 10 to the power 8. Now, now from the figure, you can see that the k transmitted along the x, which is basically this particular component, and k transmitted I should say along the z, which is basically this particular component. This is exactly this. The kt is basically the sine component, and ktx is basically the I should say the ktx is basically the sine component, and ktz is the cos component. So you can write it as ktx, which is basically kt magnitude sine of theta t, and ktz can be written as kt magnitude cos of theta t. So you have basically the kt as this direction. This was theta t, and this was kt z. So this is ktx. So this is, so when you divide it into two components, this is the cos, this is the cos, this is the sine. Okay, you're just dividing this vector into two components. And now you can write the kt magnitude can be written in terms of omega under root of mu epsilon. Now this is inside the medium. This is basically the slab. This is not the free space one. Okay, you can write it in terms of 3 square root of 20 into 10 to the power 8, which is basically omega, and you have under root of mu naught epsilon naught into epsilon r mu r. Mu r is basically 1, so you can basically solve it. You get 3 square root of 20 into 10 to the power 8 into square root of 2 divided by 3 into 10 to the power 8. So you can get, because this is speed of light, so this is 3 into 10 to the power 8. So this is approximately 2 square root of 10. So this is the magnitude of kt. Okay, now you can write ktx in terms of this. You can write it in terms of 2 square root of 10 sine of 18.43 degrees. Why 18.43 degrees? Because we obtained this theta t. So you can write ktz to be equivalent to 2 square root of 10 cos of 18.43 degrees. And this is approximately 2, and this is approximately 6. And KT is basically twice x plus, you know that when the wave was going in, coming in incident in this direction, it was going in the opposite direction, but the direction it was going is almost in it's in the same direction as it was coming. So the KT will be equivalent to twice x plus 6z. So because of these things, earlier it was how much? 4z. Now it has gone more towards the z direction. Okay, so the essential concept is that is basically the essential concept. If this was incident and this is z direction, this is x direction. So earlier it was 2x plus 4z. Now it's 2x plus 6z. Because of this refraction, it has slightly bended towards the z-axis. It has slightly bended towards the z-axis. That's why this vector in the unit vector magnitude towards the z direction goes on increasing. Okay, this is very beautiful. You see the numbers are basically giving you a lot of information. Again, if it would have been a scenario that now again this is, let's say, the slab. If the wave comes out from the slab, it undergoes another refraction, but this time away from the normal. So this refraction, it is towards the normal because it was going from a rarer medium to a denser medium. But now it's going from a denser medium and coming into the rarer medium. So it will go away from the normal. And this, if you do the same set of calculations, you will find that it will be again something like 2x plus 4z approx, because it is going away from the z axis now. So this is a beautiful way of understanding the vectors, how you can basically analyze the what information the vector is basically giving you about these moving fields. Okay, so now you find the kt to be equivalent to twice x plus 6z because you have obtained these particular two components. Now you can find the transmitted coefficient, which is basically the transmission coefficient. The transmission coefficient. Okay, let's write it as tau. You can find it as ET0 divided by E incident. That means how much it is transmitted and divided by how much was earlier incident. You can find it as twice the impedance of the transmitted media cos theta incidence divided by transmitted media impedance cos theta incidence plus theta I cos theta transmitted. You have everything. You have theta I, you have theta t, you have eta t. Once you put the values, you get basically the transmission coefficient of 0.8. That means 80% of the electromagnetic wave gets transmitted into the slab. And that means 80% goes transmitted, 20% will be reflected. Assuming that there is no absorption. There is always the absorption, but if we consider the absorption as 0, actually it's reflection plus transmission plus absorption is 1. But if we assume that it's not absorbing anything, then reflection plus transmission will be 1. So if the transmission is 0.8, then the reflection will be 0.2. That means 20% of it will be reflected. Okay, too many details in a single question. You need to just go through this question again and again. Then what you have is you can write ET0, which is basically this thing, to be equivalent to tau times EI0. So you get 0.8 times the 10, which was incident, which was earlier given in the question. This is 8. So transmitted amplitude will be 8. So you can write transmitted electromagnetic waves electric field component as 8 cos of 3 square root of 20, which is omega t, 10 to the power into 10 to the power 8, which is omega t, minus 2x minus 6z into the y cap, which will be basically the direction of the polarization of this. And essential thing here is this particular thing, which will be the k. So this is a negative sign, so it will be exactly minus, it will make it twice x plus 6z. Pardon me, just give me a moment. So the transmitted, this is transmitted. Yeah, it is exactly something like this. Yes, because it's minus 2x minus 6z. Yes. Hmm. It's going in the z direction, and yeah, that's true. Now, what else we need to find? We need to but exactly find the h of t. Now you have the e of t, you can divide it. This is pretty much easy. Now you have h of t to be equivalent to exactly the e of t divided by neta t. So you can have it, but the wave vector is basically important. You have to write it in terms of the wave vector into divided by eta t. So you can write it in terms of 2x plus 6c y cap 8 cos of, it is this y cap, 3 square root of 20 into 10 to the power 8t minus 2x minus 6c divided by 2 square root of 10 into 2266.58, which is basically theta t value. So once you solve this, you get the ht value as something around minus 28.47 x cap. You get it around this value. And if you remove this, this is the exact solution of this particular problem. So if you go through through these last problems carefully, these are very important. And if you have understood these problems, you will be able to solve these problems in the electromagnetic wave section. Particularly the final 3, 4 problems, they are very essential. If you have understood this particular scenario, you can basically understand most of the questions which come from this particular section. So it is like if you have a slab. Now the general concept is if you have a slab with certain epsilon r, with certain mu r, and certain sigma value, if let's say the sigma is not given, let's say the sigma is 0, then you have the normal, this is the normal plane, this is the normal line, and you have certain electromagnetic wave which is coming in this direction with certain wave vector which is basically k incident wave vector. Then you can always divide it into two components. You can have a z component. If this is z direction, this is x direction, and the y is going inside, then this will be the k incident of z, and this will be k incident of x, and this will be theta incident angle. Okay, and this will be theta incident angle. Okay, and and now you have certain reflections of the wave. So once it gets reflected, this will be now kt, which is basically the wave vector of the transmitted, and this will be k transmitted in the x direction, and this will be k transmitted in the z direction. You see that naturally the transmitted one, the z direction flips, it goes in the opposite direction, and now some part of it goes undergoes refraction or transmission. So this is theta transmission, or you can call it refraction, but you don't want to confuse it. Pardon me, this is not transmission, this is reflection. This is reflection. This is reflection. So these are reflection. These are transmitted ones. So this will be k transmitted. This will be k transmitted along z. This will be k transmitted along x. Accordingly, this will be theta t. So you can just divide these into two components. If this was only for electric fields, so similarly, you can find it for the magnetic fields, but you need to make sure what sort of a wave it is. If it is a TE wave, or if it's a TM wave, or if it's a TEM wave, what sort of wave is basically given. So you see that what we got as a final solution was this thing. So the transmitted magnetic field, that means this, in this particular electromagnetic wave inside the slab, there's a magnetic field, but that magnetic field doesn't have basically that magnetic field is oscillating in the y direction. This is x, this is z, this is y. That means the magnetic field is oscillating in the y direction, and this is basically giving the sense of the propagation, which is twice x plus 6c. So this is basically the k transmitted. Okay. So and yeah, and if you see, where is et? Yeah. So this is the exact magnetic field scenario. Now you cannot, if you draw the same magnetic field vectors over this figure, it's going to get messy. Then you need to basically show uh, the direction of the magnetic field the direction, the x direction of magnetic field, y direction of magnetic field, it's going to make this figure messy. So what you do is that at a time, take one of the directions and then go forward with it, but do the calculations based on the electric field, the magnetic field, and remember the impedances, which is basically the impedance of this medium, the impedance of the transmitted medium, which are basically important, and that's how you are going to approach to this particular problem. So that's it for now. I guess we have solved most of the questions, all of the questions today in this session. That'll be good. And next time we will be mostly trying to solve the questions. I cannot see anyone has entered the room today, but no worries. This video will be available on the YouTube, and you can just watch it anytime. So I'm going to end this session here. See you guys soon. Okay.